You're listening to Inside iOS Dev, show about real-world iOS development. Today with you, your hosts Alex Bush and
Andrew Rohn.
And today we are continuing our conversation, our discussion about Clean Code, Uncle Bob's book.
We're going to talk about chapters 10 through 13. Like Alex said, we've already recorded 2 other episodes. So if you haven't heard those, we highly recommend you listen to those first. Go back, do the episode list and find those. I think they're just titled as Writing Clean Code, Part 1 and Part 2. And this will be the probably final installment of the book. And again, as we've said before, we recommend you buy this book. This is just a quick overview summary of it, hitting the highlights, the TLDR, but really to learn it, I think you should read the book and dig into it and see the code examples that Uncle Bob gives. Okay, so we're going to start off with the first chapter here, Chapter 10, Classes. How do you write clean classes? First rule of classes is that they should be small.
Right.
I think in the book he also writes like the second rule is they should be small. I'm just reading off my little notes here. But yeah, classes should be small. How small should classes be? He doesn't give a prescription in terms of lines of code, but he says basically classes should follow the single responsibility principle, and that is classes should have one and only one reason to change. Reason to change. I think a lot of people forget that.
Yeah.
Yeah. So you shouldn't be having to change it for multiple different reasons.
Basically, as an example would be, say you have a service object and a storage object in your iOS code base, right? And one stores things, another one does networking. So when your storage ways you store data needs to be changed, that means only your storage changes, not your service, because service, its single responsibility is to do networking, for example.
Right. I wrote this from the book. I thought this was interesting because I often would have concerns about wouldn't there be a proliferation of like a bunch of really tiny classes, and then let's say they're all like, only 200 lines of code, 300 lines of code, they're really small. My concern was like, well, then I'm going to have a bunch of classes and I'm going to have to jump through them following this super long line of like just to find at the end what's actually happening. And Uncle Bob makes the analogy or illustrates it here. He's like, developers fear that a vast number of small single-purpose classes make it more difficult to understand the bigger picture. And he says, do you want your tools to be organized into toolboxes with many small, well-defined drawers, or do you want a few drawers you toss everything into? I thought that was a good way of thinking about it. Another thing he says is classes should be cohesive with a small number of instance variables. The more variables a method manipulates, the more cohesive it is to that class. A class in which each variable is used by each method is maximally cohesive. So, we want to be as cohesive as possible. And what that means is you're going to have instance variables or properties on your class. Let's say you have 10 methods in this class. And then you have 10 properties. If only 3 of those properties are being used, like shared between all the different methods, then it's pretty low cohesiveness. If all your methods use all 10 of those properties, then it's as cohesive as it can be. Being maximally cohesive seems like it would be a difficult goal to attain. So I think it's trying to be as cohesive as you can. And I guess this is a point he made earlier, we made in the previous episode, and it kind of relates to this. I was just writing this note here. Keeping functions small and parameter lists short can lead to a proliferation of instance variables by a subset of methods. When this happens, it almost always means there is at least one other class trying to break out of the existing class. So earlier he said clean code he made the recommendation that your parameter list, I think he said, ideally be 0 or 1 in terms of parameter list for a method. I guess 2 or 3 if it has to be, and then beyond that, you should look into maybe making a class or something to wrap around that parameter list, or something like creating an abstraction for that. But this was another concern that I had is, then if I have these short methods with these short parameter lists, I'm going to have to, like he said, create a bunch of instance variables, and then I'm going to have a proliferation of these instance variables, and then my cohesion is going to go down because I have so many of these instance variables. And then so what he says here is, yes, that will happen, just as kind of my intuition was telling me, but he says that is basically the opportunity to look at those proliferation of instance variables and say, okay, how can I create an abstraction here and like pull these out into a class? So I think that's a useful thing to keep in mind. Another thing for classes to be clean is use the open-close principle, follow the open-close principle. So that is, classes should be open for extension, but closed for modification. And just to give an example of that, we can do this by subclassing, right? If we want to modify a method, we can override it by subclassing and then providing a new implementation in a more concrete subclass. So I think that's one way.
Right. That's one way of doing open closure principle, and another one would be composition, right? When you rely on some abstraction like an interface, and then you supply the runtime various implementations of that interface. That way you also, without changing your, you open to, open to modification? No, wait, open to extension, closed to modification?
Yes. Let's see here. Dependency inversion principle. Classes should follow the dependency inversion principle. What is that? Our classes should depend on abstractions, not on concrete details. You were talking about this earlier before. Can you
Right.
Yeah.
Yeah. So essentially, what that means, dependency inversion principle is the word inversion sometimes, at least it was for me, confusing at first. What that means on a higher level, I guess, is that your higher and lower level dependencies should, higher level classes and concepts and objects should not depend on lower level, and vice versa. Instead, they all should depend on abstractions, such as interfaces.
Okay, can you give an example? Like you said, I think it was a logger example earlier, or was it like a networking?
Yeah, networking would be one of them. Essentially, let's say you're implementing a service object that's supposed to do networking and supposed to get data from the web, and then give it back to the rest of the app in the form of model objects or something like that, or some other data transfer objects. Then to do the actual networking, what would you do with dependency inversion principle and dependency injection as concrete implementation of dependency inversion? You would, in your service object, when you initialize it, you would inject an API client or HTTP client object or something like some object that does the actual networking. But instead of relying on that specific API client's type, you would rely on an interface that type adopts and implements. And that way...
That would be a protocol, essentially.
Protocol, yes.
Right.
And that way you invert your dependency, right? You instead, you don't care what is the concrete thing that's being supplied and given to you at runtime. What you care about is the interface, the abstract interface that you rely on, and whoever implements it promises to fulfill it. And that way, the benefits you get, when you ever change your one benefit, when you ever change the way your API communication happens, whether it happens through HTTP or something else, you only have to change one part of your app and recompile one part of your app, which is the actual API client part. You don't touch the service part that relied on the interface. Or another benefit you get at runtime, if you need to, for whatever reason, right? Depends on your business case and depends on the problem you solve. But for whatever reason, let's say you need to change the means of communication in your service. Instead of using HTTP client, maybe now you use Bluetooth client or something like that, right? But again, as long as they comply to the same interface, your service object can just rely on that and you can swap it on runtime.
I was a little confused on this, and then we had a conversation, and I just want to recap my confusion. Basically, my thought was, so this says to depend on some interface. And I thought, well, we supply interface. So in Objective-C, it's the .h, that would be the .h, and then Swift, it would be, your
your
public methods. So I already have that interface, and it says to depend on basically these interfaces. So I'm confused. Like, what is the benefit? Like, I have the interface already. If I wanted to change the implementation, then I would just go into the .m file or the implementation of that public method and change it. And I wouldn't have to change anywhere where any consumers of this class were using it. So I was confused.
So technically that is sort of it, right? If you're like encapsulated like that. At the end of the day, if you in that scenario though, you cannot do the runtime change because you can only have, unless you're like subclass or something, but that leads to other issues. So yeah, and in this case, you kind of have to have an interface. And if you do test-driven development, you sort of end up there naturally.
If you write unit tests, you naturally will have to end up there because you're going to have to create some
you have to stop and mock your dependencies.
Yeah.
And that way you can, the easiest way is to do it using an interface.
Yeah, I think the usefulness of an interface would become immediately obvious if you're writing unit tests because of the stubbing and mocking, like you said. But the thing is, no one really tests in the iOS world.
You should.
So I think that's why it was a little harder for me to wrap my head around. But yeah,
I think the easiest, I guess, where it's glaringly obvious where it benefits you, kind of two scenarios. Again, aside of tests. Where one scenario is where at runtime you have to swap behavior and change it. Again, maybe networking is not a good example, but storage could be a good one, right? When let's say you have a storage in memory storage and on disk storage, right? In files or core data or something. You can have two things that implement a storage interface, but just again, one saves in memory, another one on disk, and then the rest of your app kind of rely on one or another and swap them on the go as necessary. Maybe in one case you cache temporarily, so that's in memory. In another case you cache permanently, so that's on disk. And that's where your dependency inversion will kick in, right? Because, well, it gives you that, right? Because of the protocol.
Okay, I think we should move on here because we've spent quite a lot on this one chapter. Okay, so let's do chapter 11, systems. This chapter I felt was quite honestly probably the one that I understood the least. So I'm going to try to talk about this. I did try to write some notes. I actually had to go online and do a lot of reading and check out other presentations on this chapter to learn more. But I'll try my best. But basically, this chapter considers how to stay clean at higher levels of abstraction, and that is the system level. He says software systems should separate the startup process when the application objects are constructed and the dependencies are wired, he has in scare quotes, together, from the runtime logic that takes over after startup. You have something to say? Another point he says is we can use the abstract factory pattern to give the application control of when an object gets created. I think this is also related to the previous point of creating things.
Okay. Mm-hmm.
He says a powerful mechanism for separating construction from use is dependency injection, the application of inversion of control to dependency management. An object should not take responsibility for instantiating dependencies itself. Instead, it should pass this responsibility to an authoritative mechanism, thereby inverting the control. He says, another point I have here is, it's a myth we can get systems right the first time. Instead, we should implement only today's stories, then refactor and expand the system later. He says, another point, an optimal system architecture consists of modularized domains of concern, each of which is implemented with plain old objects. This architecture can be test-driven, just like the code. And then another point he says, when developing systems, is use the simplest thing that could possibly work now. And yeah, so these bullet points that I wrote for this chapter, I feel like are really abstract, and I honestly feel like that's because I really still don't 100% understand this chapter. I think this is a chapter that I'll come back to in maybe 6 months to a year and reread it and feel like I can understand it a lot more.
To me personally, when I read that, and he kind of sort of touches upon that actually even more in his next book, Clean Architecture, which we'll hope to talk about it in future episodes too. But to me, it again boils down to dependency inversion and relying on interfaces. That's kind of what it's all about. So that you don't couple anything to anything, hopefully. And when you make changes, they only happen in this one small place and don't force you to recompile and change everything else that's dependent on that.
All right. Okay, moving on. Chapter 12, Emergence. This is another chapter where the notes are a little sparse. I basically took this as a way from this chapter. It was mostly about Kent Beck's 4 rules of system design as being significantly helpful in creating well-designed software. And I'm just going to go over, all I did in my notes for this chapter was list the 4 rules that Kent Beck recommends. So he says, run all the tests. The more tests we write, the more we use principles like the dependency inversion principle and tools like dependency injection, interfaces, and abstraction to minimize coupling. Writing tests leads to better design. 2, contains no duplication. Duplication is additional work, risk, and complexity. 3, express the intent of the programmer. The clearer the author makes his code, the less time others have to spend to understand it. Finally, 4, minimal classes and methods. In an effort to make our classes and methods small, we might create too many tiny classes and methods. We want to keep the overall system small. The rule is of lowest priority. The rule of this is weird. The rule is of lowest priority. So this rule is the lowest of priority of the compared to the other 3, and should not come at the cost of the other 3 rules. That's pretty much it. I don't know. That's kind of what I took from it. Maybe other people might get something different from it.
Write tests.
Yeah, that's probably one big lesson. Okay, cool. Chapter 13, the final chapter we're going to cover today here. Concurrency. He says here, I have the first note. Concurrency is a decoupling strategy. It helps us decouple what gets done from when it gets done. This can dramatically improve both throughput and structure of the application. And then some notes about concurrency, what kind of it is, what it could help with. He says concurrency can sometimes improve performance, not always, sometimes improve performance. Concurrency is complex and difficult to implement. Yeah. Concurrency has hard to reproduce bugs. Yeah. Concurrency often requires change in design strategy. Yeah. With concurrency, it says follow the single responsibility principle. I thought this was interesting. Separate thread-aware code from thread-ignorant code and test it in isolation. I thought that was interesting. I think it's because testing threaded code, concurrent code is it could be difficult, and you test it in its own way. It breaks in very unique ways that are very hard to reproduce, and if you separate it out, I think it makes it easier to test.
Just as a side note, this is why I love RX Swift and similar frameworks that help you model time. They help specifically with that thing. You can, roughly speaking, execute all of your operations they're treated like an async operation, even though they might be executed synchronously. And in your tests, you could just run them synchronously and verify everything and assert. And then in your code, you run them concurrently on different threads.
Okay, what other notes do I have here? Know the possible sources of concurrency issues, and some of these are shared data or using a common resource pool. Another point he says here, sometimes making copies of objects to avoid synchronization is faster. So when you, let's say you have some shared object and many threads are accessing this shared object. Let's say some simple data structure, and they're mutating them, removing things, adding things, changing them. You're gonna have to synchronize the thread so they're not leaving the data in a bad state because you didn't properly synchronize the threads. But there's a cost, right? Threads might wait on the other threads to finish, things like that. There's an overhead for that. And he says sometimes making just say, you know what, I'm just going to make an entirely new copy of this object and then mutate it in whatever way I want can be faster. That's something that should probably be, you should probably profile that to see if that's the case, but that's something to keep in mind. Another thing I wrote here, concurrent code creates lots of one-off bugs that are hard to track down. Run your thread-related code in many configurations and environments repeatedly and continuously. Yeah, I feel like the concurrent code creates just like those bugs that are really hard to reproduce. So you have to kind of test them differently than your other kind of single-threaded code, I guess. And that's it. So I feel like we're done here in our clean code saga. So there's still chapter 14, 15, 16, and 17. Chapter 14, 15, and 16 give code examples that illustrate everything we've discussed in these 3 episodes going over this book, and I really think that those are very useful because this is all we're just kind of discussing it, and then in those chapters he actually implements and gives examples of how to apply these things that we've been discussing, and I think that is really useful, and you should check out the book for that. Chapter 17 is a list of smells and heuristics, and he's kind of created a nomenclature and named some common smells and heuristics in your code. I also think that's really useful. It's kind of like a reference thing that you can like read up on, and then when you're in your code, be like, oh, this reminds me of smell whatever that Uncle Bob described. So I think that's really useful. But that's pretty much the book. Thanks very much, guys, for listening. Find us on insideiosdev.com and reach out to us on hello@insideiosdev.com on email.
And use those new 280 characters on Twitter to tweet at us.
Okay, guys, take care.
Bye.
Bye.